Camille Cornett, and this is Lab 5 for Physics 2211. The purpose of this lab is to find the falling motion of the slinky and to construct a model in GlowScript. The motion was tracked using Tracker, and the video I used was from Veritasium. The results, the model used two calculations, one for after the bottom of the slinky fell and one for before, and overall the model moderately accurately predicted the motion of the falling slinky. Some physics problems and principles used in this lab were from Newton's second law, force equals mass times acceleration, or the change in momentum over the change in time. The position update formula was used when plotting the position of the slinky, and the velocity update formula was also used. The force of drag was used for after the slinky started to fall, and it is listed above. Also, the force of gravity and the force of the spring. These are the calibrations I made in Tracker to accurately track data. I used a height of 1.75 meters for the man on the left, and I plotted my axis as shown. The initial conditions were the slinky had a mass of 0.218 kilograms, an initial position of 6.57 e to the negative 2 in the x dimension, 0.481 in the y dimension, and 0 in the z direction. The initial velocity was 0 as the slinky was not moving. These are the initial conditions for the code. As you saw above, the velocity, the mass, and the position are listed. The drag constant b was used through checking and guessing, and this is a number that I ended up with. This is the code I used to track the slinky falling before the bottom of the slinky fell. So as you can see, the force of tension of the slinky and the force of work done by the slinky are inverse. So in the model, the slinky doesn't move. F net is 0. Then the slinky is plotted. So up until this point, in the y direction, the bottom of the slinky does not move. For the second part of tracking the slinky's motion, the F net is not 0. So the force of drag and the work done by gravity are not equal to 0 when added together. The work done by gravity is greater, so the slinky ends up falling. This is where we see on the graph, which we'll see on the next slide, that the slinky in the y direction has begun to fall. The graph on the left is taken from GlowScript, and it is very linear. It doesn't have many discrepancies, and the one on the right was taken from the observed data. If we look, we can see that both models are moderately similar. There's some discrepancies, but overall we can say that the GlowScript predicted model is quite accurate. Some potential error may include the drag constant or drag formula. The drag constant was found just using guess and check, which is not the most accurate method. Human error, my error, could be incorporated into it as in Tracker if I tracked something wrong, or any other general mistakes I may have made may have led to differences in the observed model and predicted model. But as for the bigger picture, why is the slinky's motion different than a typical falling object? If you were to drop, let's say, your phone, for instance, it would go down the second that you let go of it. But in this specific instance, the slinky has two forces acting on it, one of them being gravity and the other one being the force of the slinky. The force of the slinky is directly inverse to the force of gravity. So until the slinky's force tension is 0, the bottom of the slinky does not begin to fall.